Mass spectrometry. Definition of mass spectrometry. Mass spectrometry, MS. An analytical technique by using mass spectrometry for the determination of the composition of a sample or molecule and elucidation of the chemical structures of molecules, such as peptides and other chemical compounds. Mass spectrometry has been described as the smallest scale in the world, not because of the mass spectrometer's size but because of the size of what it weighs. Molecules can work out molecular structure. Chemistry 101. Mass of each group is the combined mass of the atoms forming the group, often unique. For example, phenyl, C6H5, mass equals 77, methyl, CH3, mass equals 15, etc. So, if you break molecule up into constituent groups and measure the mass of the individual fragments, using MS, can determine what groups are present in the original molecule and how they are combined together. Can work out molecular structure. What is mass spectrometry? Mass spectrometry is a powerful technique for chemical analysis that is used to identify unknown compounds, to quantify known compounds, and to elucidate molecular structure. Principle of operation. A mass spectrometer is a molecule smasher. Measures molecular and atomic masses of whole molecules, molecular fragments and atoms by generation and detection of the corresponding gas phase ions, separated according to their mass-to-charge ratio, MZ. Measured masses correspond to molecular structure and atomic composition of parent molecule, allows determination and elucidation of molecular structure. What is mass spectrometry? May also be used for quantitation of molecular species. Very sensitive technique, works with minute quantities of samples, as low as 10 to 12 grams, 10 to 15 moles, and is easily interfaced with chromatographic separation methods for identification of components in a mixture. Mass spectrometry provides valuable information to a wide range of professionals, chemists, biologists, physicians, astronomers, environmental health specialists, to name a few. Limitation: is a destructive technique, cannot reclaim sample. What is mass spectrometry used for? Chemical analysis and identification. Some typical applications: environmental monitoring and analysis, soil, water and air pollutants, water quality, etc. Geochemistry, age determination, soil and rock composition, oil and gas surveying. Chemical and petrochemical industry, quality control. Applications in biotechnology. Identify structures of biomolecules, such as carbohydrates, nucleic acids. Sequence biopolymers such as proteins and oligosaccharides. Determination of drug metabolic pathways. How does it work? Generate spectrum by separating gas phase ions of different mass-to-charge ratio, MZ. M equals molecular or atomic mass, Z equals electrostatic charge unit. In many cases, such as small molecules, Z equals 1. Measured MZ equals mass of fragment. What is a mass spectrometer? Many different types, each has different advantages, drawbacks and applications. All consist of 4 major sections linked together: inlet, ionization source, analyzer, detector. All sections usually maintained under high vacuum. All functions of instrument control, sample acquisition and data processing under computer control. Data system and computer control is often overlooked. Most significant advance in MS allows 24/7 automation and development of modern powerful analytical techniques. What is a mass spectrometer? All instruments have sample inlet, ion source, mass analyzer, detector, data system. How does it work? Plus 4000 V0 VEEEE accelerate separate. Ionize. Plus 4000 V. 0 V. E. Magnetic and or electric field. E. Plus. plus heavy, vacuum, light, vaporize, E plus A, E, sample, plus B plus C, A plus, B plus, C plus. Mass spectrometry. E. Mass spectrometer equals greater than. Analyzer types. What is the analyzer? Analyzer is the section of instrument that separates ions of different MZ. Many different technologies. Magnetic sector, quadrupole, ion trap, TOF. All based on momentum separation. Analyzer types. What is the analyzer? Analyzer is the section of instrument that separates ions of different MZ. Many different technologies. Magnetic sector, quadrupole, ion trap, TOF. All based on momentum separation. Analyzer types, magnetic sector. Easiest conceptually to understand. Separate electromagnetically. Electromagnetic prism. Usually combined with the SA, energy focusing device, enables high mass resolution, double focusing instrument, makes high accuracy mass measurements possible. Large, heavy, expensive to operate. Comparatively slow scan rates. High skill level required to operate and maintain. Self-service use by users not possible. Mass spectrometer instrument design. Different types of ionization source. A, C, Fab, ESI, MOLDE, UPSI, DESI, DOT. Also sources for inorganic analysis, ICP, GD, etc. Different types of analyzer. Magnetic sector, quadrupole, ion trap, TOF. Different sources and analyzers have different properties, advantages and disadvantages. Selection of appropriate ionization method and analyzer are critical and defines MS applications. Wide range of MS applications. Ionization methods. Electron bomb ionization, A. Chemical ionization, C. Field ionization, Phi. Matrix-assisted laser desorption ionization, MOLDE. Fast atom bombardment, Fab. Electrospray ionization, ESI. Electron bomb ionization, A. Sample is heated and energized by a beam of electrons, usually gives a molecular ion, M+, and a lot of fragments, electron bomb ionization, A. Properties of a hard ionization. Gas phase molecules enter source through heated probe or GC column. 70 electron volts. Electrons bombard molecules forming M+ ions that fragment in unique reproducible way to form a collection of fragment ions. A spectra can be matched to library STDSC, soft ionization. Higher pressure of methane leaked into the source, Inter. Reagent ions transfer proton to analyte. Chemical ionization, C. Electron ionization leads to fragmentation of the molecular ion, which sometimes prevents its detection. Chemical ionization, C. A technique that produces ions with little excess energy. Thus this technique presents the advantage of yielding a spectrum with less fragmentation in which the molecular species is easily recognized. Consequently, chemical ionization is complementary to electron ionization. Chemical ionization, C. Properties of C. Disadvantages. Advantages. No fragment library. Need volatile sample. Need thermal stability. Quantitation difficult. Low mass compounds. Less than 1000 AMU. Solids probe requires skilled operator. Advantages. Parent ion. Interface to GC. Insoluble samples. Field ionization, Phi. Field ionization, Phi, is a method that uses very strong electric fields to produce ions from gas phase molecules. Plus V less than 1 mm, field ionization, Phi. Matrix-assisted laser desorption ionization, MALDI. Sample is co-crystallized with a matrix and then irradiated with laser. MALDI is achieved in 2 steps. In the first step, the compound to be analyzed is dissolved in a solvent containing in solution small organic molecules, called the matrix. The second step occurs under vacuum conditions inside the source of the mass spectrometer. Properties of MALDI: good solubility. Vapor pressure must be sufficiently low to maintain vacuum conditions. Viscosity must allow diffusion of the analyte from the bulk to the surface. Polar, to solvate and separate preformed ion. Less sensitive to salts. Lower practical detection limits. Easier to interpret spectra, less multiple charges. Quick and easy. Higher mass detection. Higher throughput, greater than 1000 samples per hour. Principle of MALDI. MALDI mass spectrometry has become a powerful analytical tool for both synthetic polymers and biopolymers. Fast atom bombardment, FAB. Softer than A and C. Ions are produced by bombardment with heavy atoms. Gives M plus H plus ions and little fragmentation. Good for more polar compounds. Hour plus E hour plus acceleration, 5 to 15 keV. Hour plus plus hour plus hour plus. Fast slow plus 8 keV. Fast slow. Properties of FAB: disadvantages, advantages: no fragment library. Solubility in matrix, MNBA, glycerol. Quantitation difficult. Needs highly skilled operator. Relatively low sensitivity. Advantages: parent ion. High mass compounds, 10,000 AMU. Thermally labile compounds, RT. Electrospray ionization, ESI. Electrospray is abbreviated to ESI. Ampoule is sprayed out of a narrow nozzle in a high potential field. Generates positive, M plus NHN plus and negative, M, NHN ions and almost no fragmentation. Generates multiple charged ions. 2. Principle. Needs solubility in polar solvent, MeO, ACN, H2O, acetone are best. Properties of ESI. Advantages: electrospray ionization can be easily interfaced to LC. Absolute signals from electrospray are more easily reproduced, therefore, better. Quantitation. Mass accuracy is considered better. Multiple charging is more common than MALDI. Disadvantages: no fragmentation. Need polar sample. Need solubility in polar solvent, MeO, ACN, H2O, acetone are best. Sensitive to salts. Suppression. Types of mass analyzers. Magnetic sector analyzer, time of flight analyzer, TOF, quadrupole analyzer, Fourier transform, ion cyclotron, magnetic sector analyzer. Magnetic sector analyzer uses electric and or magnetic fields to separate ions. Principle of magnetic sector analyzer. The ion source accelerates ions to a kinetic energy given by half m2 equals zv, where m is the mass of the ion, v is its velocity, z is the charge on the ion, and v is the applied voltage of the ion optics. Principle of magnetic sector analyzer. Only ions of mass-to-charge ratio that have equal centripetal and centrifugal forces pass through the flight tube. It shows that the MQ ratio of the ions that reach the detector can be varied by changing either the magnetic field or the applied voltage of the ion optics. In summary, by varying the voltage or magnetic field of the magnetic sector analyzer, The individual ion beams are separated spatially and each has a unique radius of curvature according to its mass/charge ratio. Advantages: double focusing magnetic sector mass analyzers are the classical model against which other mass analyzers are compared. Classical mass spectra. Very high reproducibility. Best quantitative performance of all MS analyzers. High resolution. High sensitivity. 10,000 mass range. Linked scan MS/MS does not require another analyzer. Disadvantages: applications require skilled operator. Usually larger and higher cost than other mass analyzers. Difficult to interface to ESI. Low resolution MS/MS without multiple analyzers. Applications: all organic MS analysis methods. Accurate mass measurements. Quantitation. Isotope ratio measurements. Time of flight analyzer. TOF analyzer. Ions are accelerated through a flight tube and the time of light to the detector is measured. Ions are accelerated and their time of flight to the detector is measured. Principle of TOF analyzer. Uses a pulse of ion mixtures, not steady stream. Ions accelerated into drift tube by a pulsed electric field called the ion extraction field. Drift tube is usually 1 to 2 meters long, under vacuum. Ions traverse the drift tube at different speeds. L, T, equals V equals 2ZV, m². Advantages of TOF analyzer. Good for kinetic studies of fast reactions and for use with gas chromatography to analyze peaks from chromatograph. High ion transmission. Can register molecular ions that decompose in the flight tube. Extremely high mass range, greater than 1 m. Fastest scanning. Disadvantages: requires pulsed ionization method or ion beam switching. Duty cycle is a factor. Low resolution, 4000. Limited precursor ion selectivity for most MS/MS experiments. Applications: almost all MALDI systems. Very fast GC/MS systems. Quadrupole analyzers. Quadrupole analyzers, ions are filtered or trapped in a device consisting of several metal rods using specifically tailored electromagnetic fields. Quadrupole analyzers electric/magnetic fields trap, store, eject ions. Requires an inline quadrupole to act as Mass pre-filter. Contains a single ring electrode and a top and bottom cap electrode. Varying RF frequency will vary the MZ ratios that are trapped. Additional fragmentation can be performed on ions stored in the ion trap. Easy to use, simple construction, fast. Advantages: easy to use, simple construction, fast. Good reproducibility. Relatively small and low-cost systems. Quadrupoles are now capable of routinely analyzing up to a MQ ratio of 3000, which is useful in electrospray ionization of biomolecules, which commonly produces a charge distribution below MZ 3000. Disadvantages: low resolution less than 4000. Slow scanning. Low accuracy, greater than 100 parts per million. Applications: majority of benchtop GC/MS and LC/MS systems. Separation of proteins and other biomolecules with electrospray. Sector: quadrupole hybrid MS/MS systems. Fourier transform ion cyclotron resonance (FTICR) analyzers. Most mass spectrometers use superconducting magnets, which provide a relatively stable calibration over a long period of time. Although some mass accuracy can be obtained without internal calibrant, mass accuracy and resolution are inversely proportional to MZ, and the best accurate mass measurements require an internal calibrant. Unlike the quadrupole ion trap, the FT mass spectrometer is not operated as a scanning device. Advantages: the highest recorded mass resolution of all mass spectrometers, greater than 500,000. Very good accuracy, less than 1 part per million. Well suited for use with pulsed ionization. Methods such as MOLDE, non-destructive ion detection, ion remeasurement, stable mass calibration in superconducting. Magnet FT systems. Disadvantages: expensive, requires superconducting magnet. Subject to space charge effects and ion molecule reactions. Artifacts such as harmonics and sidebands are present in the mass spectra. Many parameters, excitation, trapping, detection conditions, comprise the experiment sequence that defines the quality of the mass spectrum. Generally low energy SID spectrum depends on collision energy, collision gas, and other parameters. Applications: ion chemistry, high-resolution MOLDE and electrospray. Experiments for high-mass analytes. Laser desorption for materials and surface. Characterization: the mass spectrum presentation of data. The mass spectrum is presented in terms of ion abundance versus Me ratio, mass. The most abundant ion formed in ionization gives rise to the tallest peak on the mass spectrum. This is the base peak. Base peak, Me43. Presentation of data. 3. All other peak intensities are relative to the base peak as a percentage. 4. If a molecule loses only one electron in the ionization process, a molecular ion is observed that gives its molecular weight. This is designated as M+ on the spectrum. M+, Me114. Presentation of data. 5. In most cases, when a molecule loses a valence electron, bonds are broken, or the ion formed quickly fragment to lower energy ions. 6. The masses of charged ions are recorded as fragment ions by the spectrometer. Neutral fragments are not recorded. Fragment ions. B. Determination of molecular mass. 1. When a M+ peak is observed, it gives the molecular mass, assuming that every atom is in its most abundant isotopic form. 2. Remember that carbon is a mixture of 98.9% 12C, mass 12, 1.1% 13C, mass 13, and less than 0.1% 14C, mass 14. 3. We look at a periodic table and see the atomic weight of carbon as 12.011, an average molecular weight. 4. The mass spectrometer, by its very nature, would see a peak at mass 12 for atomic carbon and a M+1 peak at 13 that would be 1.1% as high. We will discuss the effects of this later.